least I like to. We gotta keep my face on top. It's an ego thing. So, we learned last time how to do proportional control, right? I'm not forgetting and like imagining that we did that. We actually did that, right? We did an example.
I don't know. There's like blank spots on my page there. Like this.
I don't know what to tell you about that. I think that might just be a spacing thing.
Okay.
I don't know. Yeah, I can't control all of the white space.
I don't remember seeing that. Yeah, sure.
But yeah. Sorry?
I think we're still working through the MATLAB script.
Were we? I thought we finished it. Yeah, we got to those graphs, and we talked about the percent overshoot and all that. We chose the gain. Yeah. Okay. That was so we did do it. I will we rewind the tape, but I'm pretty positive that we did it, and we can go back and get the script. I think I sent it out, but if I didn't send out the script that I used, then I'll do that. So that was proportional control, right? Just a gain that we adjusted. We drew our root locus, and we said, oh, okay, what gain do we need to have certain performance requirements happen in this closed loop? And that was our whole approach. But we were restricted to closed loop poles being on that root locus plot, right? They had to be somewhere on the root locus that existed. We couldn't move the root locus around. So if our performance criteria cannot be achieved on the root locus, then we're screwed, right? We're totally screwed. So there are some techniques for changing the root locus to satisfy those requirements. Okay, and that's what we're going to do in the rest of this class is change the root locus to make it go through the points that we want and therefore give us the performance that we desire out of it. So we consider two classes of controller: PID, proportional integral derivative controllers, and proportional lead lag controllers. PID controllers use ideal integrators, s to the minus 1. So remember, integrators are in the transfer function a factor of 1 over s, right? And differentiators s, and so we'll talk about those some more. And therefore require active circuits for instantiation. So PID requires active circuits, so you got to have like an op-amp or something like that in there. Proportional lead lag controllers can be considered approximations of PID controllers, and these can be realized in passive circuits, so some advantage in certain applications for that as well. But we will build controllers incrementally by cascade compensation. This means we will begin with proportional controller design. So let's remember what that looks like. So that looks like we have a command R, summing junction, and we're going to go into our controller and what I'm going to do here is give myself 3 blocks for my controller, and I'll explain that in a moment. And then I'm going to go into my plant, right? So there's my plant transfer function, and it's got, G in there, whatever the plant is, an output, and then let's just assume for now unity feedback, like this. And so when we do the gain control like that, so what we finished doing, so this is output y. What we finished doing last time was we put a gain here, k, and we move the gain around, and then so we'll just put a 1 in these blocks to start, and then we're going to change that in a second. We put a gain there, and we adjusted it based on where we showed up in the root locus for that gain, right? That was what we started with. Now we're going to use cascade compensation and put other controllers in here. So these are going to be cascade compensators. And we're not going to just put 1 in here now. So with game controller, they're just 1s. But with other types of control like PI, PID, lag, lead, these are other transfer functions. So I'll just call this like C1 of S and C2 of S. So there are going to be some transfer functions we're going to put in there, very special transfer functions that we design to make the system perform the way that we want. And that's what brings about this terminology of compensation. So in the end, this block here, so these are the cascade compensators. In the end, this whole block together, if you combine these things into one transfer function, it would just be called a controller, okay? And that controller would have transfer function k, c1 of s, c2 of s, combining the three together. So that's the difference. Sometimes people talk in terms of compensation. Sometimes people talk in terms of controllers. And what they mean is the controller is the whole thing together. Compensator is thinking about sort of incrementally building up these cascade compensators. And that's the approach we're gonna use. So for instance, we will begin with a gain controller design, which is what we start with in all of the different methods that we'll use. We always start with a P controller, and then we cascade an integral compensator. So now the controller becomes a PI controller. So we put in an integral cascade compensator, and now between the original proportional controller and now with this cascade compensator of the integral control, we now have a PI controller. And finally, if we wanted to go all the way to a PID controller, we could cascade a derivative compensator, and then it would become a PID controller if you combine them all together. So that's what we're going to do. We're going to learn 4, so PI, PD, PID, 6 types of controllers, but they're all very similar. So we're going to learn the first non-gain controller, just simply proportional controller today, and then we will go on to the other types next week. Thank God. And yeah, so this figure took me a long time, but it was worth it. I'm proud of it though. I think it looks real nice. So we're going to learn how to do PI controllers first. Okay? When studying steady-state error, we discovered that the more integrators in the open loop transfer function, the better the steady-state error, right? That was like the big conclusion that we came to. More integrators, better steady-state error. Fewer integrators, worse steady-state error. It depends on what the command is too, right? If it's a step command, or if it's a ramp command or parabolic command. We went through those considerations. But at the end of the day, it was always more integrators, better steady state error, fewer integrators, worse steady state error. So what the PI controller does is it just plops an integrator into the forward path transfer function, into the open loop transfer function. Okay? Easy enough. The real trick comes in not affecting the transient response too much when you do that. Okay? And we'll learn how to do that. So so later we're going to deal with how to design for transient response, but PI controllers, you can do transient response design with your gain, with your P, right? But we can't move the root locus still very much. We will a little bit with the integrator, but not very much. We're trying not to affect it because our PID design method is to affect steady state. So affect steady state with the integral term, steady state error, and then affect transient characteristics with the derivative term. So we're going to try to not affect it too much with the integral because we're going to affect it a lot with the derivative. So we're aiming for steady state error control mainly, but also we can do a little bit of work with the proportional controller too for the transient. So here's the plan. Include an integrator, which is also just a pole at the origin, in the controller, and a nearby zero to counter the pole's slowing effects on the transient response. So if you just plop an integrator in there, it has a significant effect on the transient response. It totally changes the root locus plot. Okay? And you can imagine, you guys know the construction rules, it's going to totally change how the root locus branches occur, like on the real axis initially, but then also everywhere else. So, and usually the effect is to slow the response when we put an integrator in there. And we don't want that. We don't want it to slow the response. So let's learn how to do that. And really the key is to just put a zero in there as close as possible to that pole with some constraints, and we'll explain what those constraints are. So why does the integrator affect the root locus and therefore the transient response? So adding a pole at the origin completely changes the root locus and therefore the location of the closed loop poles and therefore the transient response. In order to mitigate this, we place a zero near the origin, which nearly cancels the integrator's effect on the root locus. To see why that cancellation occurs, let's recall that the root locus must meet the angle condition, the angle criterion. Remember that? So, where's my pen? There it is. So let's look at this figure to try to figure that out. So let's say you had a system that just had 3 poles in the open loop originally. So this pole, and this pole. And you drew its root locus. Okay, so we're ignoring these two for right now. We're going to march along the real axis. No locus, no locus. Okay. Locus, no locus, no locus. Locus, right? So that one goes off there. There are going to be 3 asymptotes, and they're going to go off at these angles here, and the root locus will look just like the green plot did, right? Look just like that. Now, let's say you included your compensator. I'll use a different color for the compensator. We'll use purple. So say you put an integrator at the origin, so an integrator in your transfer function. That pole right there is going to totally change this root locus if we don't add a 0 there as well. Still will change it, but not as much. So let's put a 0 nearby. This is our method, right? And we can re-sketch the root locus. Notice that this is going to be in there, so no locus, locus, no locus, locus. So it didn't really change the real axis that much except for add in this little chunk here. And this actually is going to look the same too. And the reason for that, let's think about the angle criterion for this. You can draw a vector from each of these poles and zeros to a test point on the root locus. And at every point on the root locus, the angle criterion has to be satisfied. The angle criterion is that if you sum the angles from the zeros and you subtract the angles from the poles, you have to add up to pi, right? 180 degrees plus or minus 2 pi times whatever. So that means that we should be able to take, and I wrote it down here, but I realized when I woke up this morning that all of these signs were wrong. Do you guys have that happen to you too? Where like you don't recognize a mistake until you wake up in the morning, and then like you remember back to something and you're like, that was wrong.
Always halfway to school, too.
Yeah. Happens to me all the time.
The second you walk out of the test.
So theta 1 comes from the angle that the vector that starts at this pole and goes to this test point, the angle between that and the real axis, and so that's theta 1. It's a pole, so it has a negative contribution, right? So negative theta 1. And then theta 2 is the only zero, and it has a positive contribution. So that is plus theta 2. And then all of the other angles are negative because they're all poles, right? So this is minus, this is minus, this is minus. Okay? So that sum has to equal 180 degrees plus or minus 2 pi, multiples of 2 pi, integer multiples of 2 pi. So what happens if theta 1, what happens if the pole and the zero are close to each other? How are theta 1 and theta 2 related? Yeah, they're very, very similar to each other. And so their angle contributions have opposite sign, right? And so they cancel, virtually cancel. They don't completely cancel, but they virtually cancel. And therefore, we shouldn't affect the root locus that we had very much, as long as they're close. So that's sort of like the aha for integral compensation, is that we can get the steady state error improvement by adding the integrator without really affecting the transient response that much, without really affecting that root locus that much. So, but one thing we are doing, and it's important to keep this in mind, we are adding a pole to this system that a closed loop pole is going to end up somewhere on this little branch here, right? It's got to. That's where there's root locus. So there's got to be a pole somewhere, a closed loop pole that shows up there that wasn't there before. So there's a new closed loop pole in the system. And notice that it's pretty far right. Remember, we can ignore the ones that are far left, out in the complex plane. Your left. Out in the complex plane. But ones that are close to the real, or to the imaginary axis are significant to the transient response, well, to the response as a whole. And we are introducing one here that is most likely going to be closer to the real axis than those, what we hopefully have a dominant poles, right? So that is a real effect, and we'll see how that effect manifests itself in the example. Essentially, this creates the transient response will look about the same as it did before, but there will be this slow steady state error decrease that happens. It doesn't happen at the same speed as the transient happens. It happens slower, and that's because this closed loop pole is so close to the imaginary axis that it sort of oozes back. So the steady state error compensation, if you don't want to affect the transient too much, is going to be a slow response. If you don't mind if it affects the transient response more, you can move this 0 leftward, okay, which is going to pull the closed loop pole leftward, and it'll make that steady state error oozing faster. So the steady state error will close faster, but the price that you'll pay is that the transient's going to change. And that might be okay for your application, but if you don't want to affect it at all, then you need to keep the 0 pretty close to this axis. So, all right, let's play with it. Let's see what happens with an example. We'll do the design procedure I include just to give you guys something concrete to work off of, a sort of a recipe to start. So the following can guide us through this typically straightforward controller design. So step 1, design a proportional controller to meet transient response requirements by choosing the gain K for the dominant closed loop poles to be P1 and P2. So this is the exact process that we used to design our proportional controller last time. Right? So we do that again. And then step 2, include the integral compensation and put a real 0. Here's a place to start for placing your 0. So a lot of times people are like, where do I put it? Like, I don't know where to put it. This is a sort of reasonable place to start with the placement of your 0. It's just take the real part of your dominant closed loop pole pair and divide it by 10. And so you're 10 times closer to the real axis than your dominant pole pair. That is just a sort of a made-up number, though. You can place it wherever you want. It's just a place to start with your design. And you can iterate from there. Or you can just say, screw it. I'm just going to place my 0 at negative 0.5. Do it. That's fine. That is totally legit. So, step 3, tune the gain, K, such that the closed loop poles are as desirable as possible. So you have to retune the gain afterwards, because you are going to affect that root locus a little bit, so you have to retune. And then step 4, simulate the time response to see if it meets the specifications, and tune if necessary. If the steady state compensation is too slow, that sort of steady state ooze back up to the final value that you desire, try moving the 0 leftward. So if you move the 0 to more negative values, then you're going to speed that up. But you are going to affect the transient response as well. So that's the point that you have to start to feel the trade-off and decide where you want to end up. So this is sort of a fluid process. So let's do the example then. So for a plant with transfer function 10 over s plus 2 times s plus 5, design a unity feedback gain controller such that the system has 20% overshoot and 0 steady state error for step inputs. Okay, so the first thing before we go over to MATLAB, let's recognize what the steady state error is for this system to begin with. So this is the plant transfer function. And do you guys remember how we decide what the steady state error is going to be? We can go back to our table, right? But for a step input, so remember that we're using the final value theorem, right? the limit as s goes to 0 of s times the output, or it's actually the error transfer function, which is 1 over 1 plus g of s, and where this is g of s. And then times the input, which is 1 over s, is our step input. So the s's cancel, and we're going to take the limit as s goes to 0 of g of s, and we're going to end up with some finite steady state error, right? So if you plug s equals 0 in here, you're going to get 10 divided by 2 times 5, which is 10 divided by 10, which is equal to 1. So you're going to get 1 over 1 plus 2. That's our steady state error for just a unity feedback system. So that's not good. That's not what you want. So we're going to put an integrator in there, fix the whole thing. But then we got to make sure we put that 0 in there too. Otherwise, we're going to screw things up. So that's our goal. That's what we're sort of our broad plan. So let's switch over to MATLAB, and before we get to the plots, I'm going to restart MATLAB because I've done this before. So annoying to me. You know, that's like the type of thing that you're just never going to get that bug worked out. Like, they're just never going to fix that bug. It's just never going to happen. So I'm not even going to report it. Also, the Mac version of MATLAB is always like the last to get updated for bug fixes and stuff. It's kind of on the buggy side. But we make do for all the other benefits that Macs bring. Right? It's funny. They're almost like, so there's, it's like religion, politics, unions, and then like Mac versus PC. It's like that's the order of like people getting fired up about a topic. Yeah, I think that's how it goes.
Just hate Apple products.
Yeah, I don't know. I feel like there are certain things we just like draw lines in society, and it's like you're either one or you're the other. I guess Mac versus PC is one of those things. Sorry? Avocados and no avocados? Really?
Yeah. Really staunchly hate avocados.
Huh.
The same reason people like hate Anne Hathaway for no reason. It's like the same kind of thing.
Why would you hate avocados?
Right?
What did Anne Hathaway ever do? Didn't she do those Capital One commercials though?
No, that's Jennifer Gardner.
Oh yeah, her. Yeah, I like didn't have a thing being against her, but she started doing those commercials. I'm like, yeah, I don't know. I don't know if I can get down with that anymore. All right. Anyway, moving on. So let's do this example in MATLAB. We've got this plant transfer function. We should probably define it. We'll use ZPK because it's already factored out, right? So ZPK, no zeros in the plant transfer function. There are 2 poles at -2 and -5. And then the overall gain factor on this is 10. There it is. So we can do the root locus. We don't need to specify the gains. I specified the gains here because I wanted to get a little bit better resolution in the place that I care about. But the first time through, you don't need to specify your gains. So let's see what the root locus is. Not surprising, right? It's 2 poles and no zeros. So really easy root locus to draw. The only reason that we use MATLAB at all is to find what the gain, what gain corresponds to the percent overshoot requirement that we have, right? Percent overshoot requirement specifies a specific ray beginning at the origin and going outward, right? And we could think about, calculating this. I mean, geometrically, this is actually pretty easy to do because it's like a triangle, so we could do it. But we are not going to. We are just going to come in and say, oh, look, 20% overshoot occurs at a gain of 4.9. See? I like MATLAB. Okay, today we have good vibes from MATLAB today. Gain of 4.9 gives us a percent overshoot of 20%, which meets our transient spec, right? So that was our step 1 of our PI controller design procedure, is to do the transient response, and for the gain control alone, got a gain of 4.9, and I mean we could at this point like build the controller, do our simulation, see how this works. But we're going to wait to do the simulation until the end, and we'll simulate them both together. So we'll just continue on our design procedure for now. It's useful using our little like rule of thumb about where to put the 0 to specify where the real part of the closed loop pole is, the design closed loop pole is. And this one occurs at negative 3.5 in the real direction, coordinate, depends on the way you want to look at it. So negative 3.5 is something that I'm going to save in here and call it S real. All right, step 2. We're going to stick a pole at the origin. We aren't going to move where that is. Whenever we do PI control, it's always going to put the pole at the origin. With a 0, we are going to put we're going to say S real divided by 10 as a place to start. It's not bad. I mean, we could do maybe better, but it's not a bad place to start. So now we can build a system model of the compensator. The compensator is going to be a 0 divided by a pole, right? And the pole is going to be at the origin. So if we were to come back here, the compensator is going to look like S minus whatever that value is we decide to put the 0 at, divided by S, the integrator. So this is, so S minus, if we put it at negative 0.35, that corresponds to 1/10 of the way to negative 3.5, right? And that's why we chose negative 0.35. It's not a bad place to start, like I said. And now we can find the open loop transfer function. So the open loop transfer function for this system then is going to be K1, our original gain, times the compensator, times the original open loop transfer function. Okay? So if we evaluate that, we see that now we've got our original 2 poles here, S plus 2, S plus 5. Those show up there. And then we've got our original gain term was 10, right? We multiplied that by our first gain, our K1, of 4.9, so we got 49. And then we have our integrator that we put in there for integral compensation, and then our 0 that we're using to cancel out the transient effects of that integrator, right? So we've got it all combined into one open loop transfer function. And now we can do a new root locus of the open loop system with the compensator in there, okay? And hopefully, if we've done our job correctly, we don't expect that the root locus is going to change a lot, right? It's going to have that pole and that 0 near the origin, but that's mostly what the effect should be. And that's what we see, right? We see this pole and this 0 show up from our compensator, and then we see, once again, these things come together and split off. But it's hard to tell. It's a very small effect, but you can see that the root locus branches get pulled a little bit to the right. So that is something, if we got the 0 closer to the pole, that wouldn't happen. So this is going to, so it's not going to affect our percent overshoot because we can still intersect the root locus with a ray starting at the origin going outwards, percent overshoot. But if we had a settling time that was specified to be something that we couldn't affect at all, this would be kind of an issue because what is the settling time? What is the effect of settling time of pulling the root locus a little bit to the right? Is it going to be slower or faster? If we pull it to the right, it's going to be a little bit slower. Yeah, we pull. Oh yeah, towards the origin, right? We see that the root locus is pulled a little bit towards the origin, towards the imaginary axis, which corresponds to slower decays, right? So the settling time then is going to be longer, which it's not a lot, but it is a little bit longer. I mean, it's a very slight amount, but it's a little bit longer. So that's it may or may not be desirable, but so we might need to move that 0 a little bit to fix that. But let's go forward with this. We didn't affect it too much. We affected it a little bit, but not too much. So let's find our 20% overshoot again. And there it is. So this occurs at a gain of 0.94. Now, the reason that it says 0.94 and not close to 4.9 again is that we included the original 4.9 gain in the open loop transfer function for which we created this root locus. You can do this either way. So in some of the examples we'll do next week, I'm going to leave out that gain in the second root locus so that the gains will be similar. I want you to be able to do it either way. It's just recognizing which way you've chosen to do it. So this one is going to be essentially, if this gain is equal to 1, it's no different. It essentially means that there's no difference in gain from the first to the second. So if you multiply by 1, nothing happens, right? This is 0.94, which means we're close to the gain that we got before, but we've changed it a little bit to match our percent overshoot requirement. So that is 0.94 gain, and we're going to save that as K2, our second gain, and we're just going to continue to multiply by the original one. So now all that remains is to simulate and compare the two controllers, the proportional controller versus the PI controller. So we should see. So we expect that the proportional controller is going to have some steady state error, and that the PI controller is not going to have steady state error in the for a step response, right? So let's find the closed loop transfer functions, which can be found from these two commands, essentially just saying that the system 1 is the open loop transfer function with just the plant in it. And our first gain that we found, and then doing the feedback 1 over 1 plus g, or g over 1 plus g, I should say. And then the second system, the PI, we have to multiply by K2. And sys2 includes, remember, we define sys2 to include the original system and the compensator and the original gain. So all we need to multiply it by is K2. And there are, you can do this a bunch of different ways. You can not combine things until the very end. You can combine them along the way like we did. It's sort of up to you. It's a matter of taste. And then we just have the step responses left. So let's look at the step responses and decide what to do. So the blue line is the proportional controller, and the red line is the PI controller. So they look like they have pretty much the same transient response, right? I mean, they both have very similar characteristics. It's just that the PI controller is going to the final value of 1, so it's going towards 0 steady state error like we designed it to, and the other one's not. The other one's ending up with a significant steady state error, and so our design worked, but notice that the steady state error compensation is a little slow compared to everything else, right? This, it responds quickly, and then it sort of slowly oozes up. So we could move that 0 to the left more. We're going to lose a little bit of settling time. You might see, you might be able to tell mostly from zooming in on where these peaks occur. This peak occurs a little bit later. The red peak occurs a little bit later than the blue peak. And that's because we lost a little bit of settling time. They're very related, the peak time and the settling time. So we could go back and sacrifice more settling time, and we could improve this steady state compensation to make it faster. So it's sort of a trade-off, and I think that, in my opinion, I would probably go a little bit more left with that 0, so that we could get a little bit faster steady state error compensation. That would just be my personal preference. It kind of depends on the system that you're going for, though. I like to see it respond a little bit faster. But this is generally a legitimate PI control design. It's not bad. It does what you want. Depends on the system that you're implementing this on, whether this is the right response or whether one that is a little bit more aggressive with the integrator is the right response. So yeah, so that's the design. That's how you do a PI controller design. It's pretty straightforward. There's really not a lot to it because you just put an integrator in and then you put a 0 in and then you find the gains that you need. So pretty straightforward. All right, that's all for this week. I'll see you next week.